Hello, Actuate. Great to be here. And I want to spend the next 30 minutes telling you a little bit about end-to-end technologies we're building to accelerate deployment of end-to-end technologies. Myself, I'm Vijay Badrinarayanan. I'm the VP of AI for Wayve. It's a startup based in London. We're expanding quickly here in the Bay Area as well. And I've spent the last 5 years building end-to-end driving policies. So I know a few things about that. Let me start by saying we live in a really exciting and fortunate time. Here's a small end-to-end trained neural network driving through dense urban traffic in London. What's interesting here is it can interact, it can negotiate with other road users and do this very robustly. You can do this for hours on end today with no interventions. No, it needs no hand-coded rules. It's just pixels to action. No HD maps, so you don't need to scan cities. No expensive sensing. That's all camera-based. And it's really generalizable. And all of the generalizability just comes from training. Data, compute, and lots of AI smarts behind this. Right. Now, if all of this is not very interesting or impressive, what's probably striking is how quickly we've gotten to this level of performance over the last couple of years. 2 years ago, or 3 years ago, when I spoke to a lot of people in the industry, they were really big skeptics of this. They're like, end-to-end, it's not going to work. Now it's like table stakes. Oh, don't tell me about end-to-end, it's just normal. No, tell me about the rest of this stuff, right? It's the rest of the stuff I want to talk to you about. From a technical perspective, we at Wayve, we see AI evolution in 3 major phases. It's probably obvious to you, but I'll probably emphasize a few things here. The first one is the computer vision revolution. The second one, the NLP. And now, quite definitively, it's the embodied AI robotics evolution we're all part of. Now, what's common across all of these is having data, the right compute, and the right challenge as well. With computer vision, we had ImageNet, dataset, and challenge, and that gave us CNNs and ResNets. With NLP, we got common crawl, find web, etc., and we got transformers. And now, in a post-COVID world we all live in, everyone's realized that the physical industries need to be disrupted. That's manufacturing, supply chain, logistics, mobility, all of this. And interestingly, from the AI perspective, everyone's realized that you can only crawl the web so much or watch and learn from YouTube videos. It's hard and it's saturating. So you actually need physical embodiments giving you closed-loop data in the real world. So it's a really nice setup between need and from the industry, from the AI community, and the future looks really, really bright here. And stuff is beginning to work. And now, at the heart of it all are all of these end-to-end policies, basically a big transformer or a small transformer, whatever be it, train end-to-end. There's a lot of promise there. One is it's computationally homogeneous. That is, it's highly portable across tasks, across embodiments, etc. Then there's generalization through data. So all we need to do to get to a new geo is collect data and train, and it works. It's scalable economic, lean sensors. It's all about intelligence. Sensors are important, but intelligence is the most important thing. Superior safety. We focus on safety through experience. I think that's the best form of safety. Now, all of these promises are being realized today. It's not just a promise. We are at different stages of realizing this, but it's all happening today. But this is not enough. An end-to-end learned action policy is not enough to deploy products. What you need to do also is validate these policies for safety, for generalizability. You need to build the right tools to accelerate developer efficiency. We've seen a lot of those in today's talks. That's the right thing to be thinking about. Fleet data management. How do you gather data from different embodiments with all of the privacy, security issues, and how do you use that? That's a problem to solve for all of us. And finally, we need to engender trust in these systems. That's a problem we need to solve as well. So At Wayve, the focus areas for us to create embodied AI products are, at this point, three main things. One is simulation, first for validation and then for training. Two is multimodality, particularly from the perspective of data efficiency and engendering trust. These are the two things we think about when we think about language, for instance. And scale. When I talk about scale, it's the scale of deployment. So how do you do this in a cost-effective way? How do you build foundation models, et cetera? So I want to walk you through all of these and tell you what we've been up to. Now, when it comes to simulation for AVs, particularly for end-to-end learned policies, the ask is very challenging. You got to do a whole bunch of things. One is you need to render pixels which have very low sim-to-real gap. Okay? So things like Carla, which are very interesting simulators in them, so they're just not going to cut it. Two, you want to simulate dynamic and deformable scenes. And you want to do it in a very cost-effective way. You don't have LiDARs on every single vehicle on the planet, so you have to somehow do it with cameras. Three, you want to simulate the full environment and the platform. So things like Waymo's WayMax won't work. And ultimately, you also want the simulator itself to be data-driven and scalable. So somehow, it needs to be a learned simulator. And it needs to be controllable as well over the long term. So a lot of requirements from sim for if you're trying to get into end-to-end policies and trying to deploy them. So let me introduce to you Prism 1. This is our resimulation simulator for dynamic urban scenes. Here are two renderings of a dynamic urban scene, one from London and one from the Bay Area. So as you all know, the challenge with simulation is not really geometry anymore. You can do really good geometry. That's not a problem. You have nerves, you have Gaussian splatting, all this kind of stuff. You can do that really well. But it all comes down to dynamic scenes and rendering lighting and shadows and all of that kind of stuff. What we have been doing is, with Prism 1, is like, we don't want to deal with perception, bounding boxes, all that kind of stuff. It needs to be self-supervised somehow. That's the target we set. And what you're seeing here is a completely self-supervised end-to-end learned simulator. So you have networks which basically separate dynamic from static. You render the static geometry and then blend in the dynamic content. Right? That's what you're seeing here. In the past, you did this with scene graphs. So you would have to separate every single dynamic element in the scene and then model the interactions between that and the other dynamic elements in the scene. That's messy. You're going to make mistakes there. Here again, you need to go end-to-end if you really want to unlock the promise of simulation. Here's a few examples of what you can do with Prism 1. One is, of course, you want to do novel view synthesis. If you're training end-to-end policies, you must be able to simulate off-axis states. So this is where the more you can simulate with high fidelity off-axis states and the actions corresponding to it, you can go quick in terms of learning efficiency. What's impressive here and what is required as well for dense urban scenes is not just off-axis, but also high-fidelity rendering of reflections and things like that. So things like nerves and Gaussian splatting, they're doing a great job at this. So we really have the strong tailwinds from all of this tech you can throw into this. Here's another use case where you freeze position, your ego vehicle's position, and just let the sim run forwards and backwards. Right? You can quite clearly see here how we separate out the dynamic from the static, and you can render the static content with high fidelity. And when it comes to the dynamic content, you really need to pay attention to even small things like traffic light state for obvious reasons. Right? So you can see this traffic light state, reflections, all of the other deformable parts, etc. And of course, lighting is something which, if you're testing in a city like London, you need to model really, really well. Because you're going to get lots of different weather patterns through the day. And if the modeling of lighting is insufficient, you're going to get caught in the sim-to-real gap. So then, have we solved simulation? No, unfortunately. We made big strides in the right direction, and I think end-to-end is the way to do this. But we've made an impact already. We save a ton of on-road testing time by using our simulator. You can do a lot of regression testing using the simulator. But we have a long way to go in terms of using this fully for training, for instance. Right? But generative AI and neural rendering really holds a lot of promise in terms of thickening the long tail to get there. Now, what I showed you with Prism 1 is what we call world on rails. You can't do too much with it. You can do a few interesting things, but you can't control every element. You can't remove elements. You can't have dynamic elements react to the ego vehicle's actions, etc. So you want a simulator which can do that as well. So for the past few years, we've been investing quite a bit in generative world modeling. Gaia, which is our generative world model, stands for generative AI for autonomy. And this is yet another end-to-end technology which really can accelerate deployment of end-to-end policies. Here's an example where you take a transformer, you condition it on a stack of frames, and then you can control the actions. You can steer, in this example, you're going left or right, and then you can see the other agents reacting to the ego vehicle's actions. Right? This is something you really, really desire to enrich your training set and to do closed-loop validation as well. What's interesting is to train Gaia, you can basically use any video on Earth. You can just toss that. If you have enough data on compute, you can actually toss it, train it, and it'll get better. So it's fully scalable that way. The other thing you can do is not just condition on action. You can condition it on bounding boxes. You can condition it on text. You can do all of these really cool things. Here you see an example where you condition it with a 3D bounding box with pose, of course, and then it can basically render an object there. Right? This is something you would want to do. This is in painting, effectively. And here I want to show you what you're seeing here. In this video, in this multicam video, the geometry was rendered separately, and all of the objects there was completely in-painted. So this is an entirely new scene which was created element by element. So there are pedestrians, there are cars, so you can see it gets its motion right, its pose right, a lot of the reflections right, etc. So we're making some really, I think with these tools you can make some really big strides. So data compute and still end-to-end training, fairly simple transformers. It's not very complicated to do this today. It requires some AI talent, for sure, but not a great deal of complexity here. So now, with Prism and Gaia, we've been investing quite heavily into simulation for both validation and testing, and fully controllable simulation. The next thing I want to talk to you about is really multimodality. When you think about multimodality, most policies are vision to action. Now, we want to bring in language. When it comes to things like humanoids, it's quite easy to understand, or even manipulators, it's quite easy to understand how you bring language. You sort of prescribe the task, you talk to it, there's time. The latency requirements are not so severe. But when it comes to self-driving, what do you do with language? Right? It's not very obvious. But then language models have a lot of general intelligence, and you want to capture it to improve the efficiency of learning. The second thing you would probably want to do with language when it comes to driving is adaptability. You have a trained policy, you spend millions of dollars training it, probably you train a foundation model and then you distilled it and you got a policy. And you have a new scenario and you want to adapt the behavior of the model to that scenario. How do you do that? Language can sort of come in there as well. And finally, engendering trust and talking about safety and building HMIs, interesting HMIs as well. There again, language can play a big role. So we think language for driving, the promise hasn't been fully unlocked, but I think we've been pushing pretty hard at that, and at some point it's going to be very, very useful. Lingo is, I want to introduce you to Lingo. It's our grounded vision language action model. This is yet another end-to-end trained model. And Lingo can do a few things for you. It can commentate on its own actions. And these are not two different models. It's not a model which is basically looking at the actions coming from another policy and then commentating on it. It's one model which can drive, but which can also commentate and explain its actions. Now, it's also a model which, when prompted, can change behavior, and I'll show you in a second what that looks like. And this is the first vision language model on public roads today, and we test this quite regularly. So it's really, really exciting that you can do this. Here's another interesting use case for language. Here's Lingo driving in our simulator, and based on the prompt, you can change the behavior of the driving model, in this case, Lingo itself. Right? In one case, you're asking it to stop behind the bus, the other case, overtaking the bus. If you can do controlled behavior generation like this, and it gets more and more accurate, more and more controllable, your data efficiency goes up. You can toss that back into training. Right? So we managed a way to actually get language into mainstream driving, to train mainstream driving models. But the most interesting thing, and this is the thing I'm most excited about when it comes to language for driving, is what I call multimodal training. A paragraph of text may be worth 1,000 words. Imagine you have a rare sample you have to learn from. You have one sample with a batch of frames and an action. Now, if you just toss it into your policy learning, it's just not going to learn anything, or it's going to disrupt learning for other behaviors. But what you really want to do, potentially, is use language as a way to amplify the value of a data sample. You can write 10 pages of text about a video, of a sample of a video. Can you now use that to amplify the value of that single data sample? So that's the direction we're most excited about, and we're pushing quite hard in that direction. And hopefully, maybe if I'm invited the next year here, I'll tell you more about that and how that actually works. Right. Okay, so we've looked at simulation, we've looked at multimodality. Now I want to tell you a little bit about how we think about scaling embodied AI policies, end-to-end policies. How do you want to deploy them? Now, we've heard a lot about foundation models today, and I'm also going to talk about foundation models. But the reason is we want to deploy these policies in a cost-effective manner. You don't want to train something for every single vehicle type. That's just going to be too ineffective. And there's a lot of synergy between tasks as well. You can do things like Gaia, which is a world model simulator. You can do Lingo with the same model. You can drive with the same model. You can produce depth with the same model, or segmentation, or actions, whatever. Right? And you want to be able to do this across a wide variety of sensors. So the inputs can vary, the outputs can vary. And you don't want to retrain these models all the time. You somehow want this to work for a whole range of platforms, embodiments, tasks, etc. So obviously, that means you want to build a foundation model. Now, what's different to what you saw this morning is we don't believe you can just take what's out there and simply glue it and call it a foundation model. You need to engineer this from scratch, and you need to put some muscle behind the science of building a foundation model. It's not very clear just that next token prediction will be the thing for robotics. So that's something we are investing in, and hopefully something I can talk about next time around. But what I want to sort of expose you to, and this sort of came out in the other talks as well, but I'll sort of emphasize this again, is it's to build a foundation model for embodied AI, which sort of generalizes. You cannot just scrape data from the web. You need closed-loop interaction data from a whole range of embodiments. And there's a big gap in the industry. Like, we don't have a data marketplace we can go to and purchase data. So it requires building a trade between every supplier and the foundation model builder. And it's not very clear what that is. And it's something we're trying to actively work on within Wayve. Diversity, right? You want data from all different embodiments. I said that once again, as I like to say, embodied AI and foundation model building for embodied AI is not just a technical problem, it's a techno-business problem to solve. Training compute, it's going to get expensive for sure. High-dimensional video data, it's not LLMs where the input and the output dimensions are the same. This is crazy high-dimension data. If you start adding things like memory, etc., multiple cameras, multiple radars, a lot of memory, it's going to be super expensive to train. So you need the right partners there. And of course, physical embodiments, the data you're getting is just not going to be clean. You need a way to somehow use it. So you need the AI smarts to be able to do this really well. All right. It seems like I'm ahead of time. That's rare, actually. To conclude, embodied AI is quite definitely the next frontier of AI. At least for the reason being, the AI folk need data, and they're going to come to robotics, right? If not for anything else. So if they really want to see the promise of AGI happening, you got to get here. So it bodes well for all of us. So we're in the right place at the right time. I think multimodal foundation models are going to play a key role in this, and it's the natural sort of next step. And I believe that we haven't cracked it yet. From a technology perspective, it's not just taking Llama and somehow gluing a VLM and doing things like that. You really need to think about this from first principles, and how do you do this for robotics? And so AI smarts, super, super important. It's not all about just data and compute and scaling. AI smarts, super important here. And as I said, if you really want to get to the big promise of embodied AI through your products, you need deep and sustained partnerships. You need patience. It's not going to happen overnight. And you need to find interesting trades where you can get closed-loop interactions for something you're actually offering them. What is it? You need to think through those things. That's what I want to communicate. Thank you.